y'all, I'm Camille. I'm a part of Group 3, and today I'll be presenting on the experiment we did last week, which is the air conditioner. This is a brief overview of what I'm going to be going over today. Background and theory of what an air conditioning unit is, apparatus objectives from the experiment, some raw data we collected, data analysis results, and the conclusion. Okay, basically what I went over 2 weeks ago, an air conditioning unit has 4 subsystems: compressor, condenser, expansion valves, and an evaporator. And we observed how a heat pump acts as an air conditioning unit. It basically absorbs heat from a source with low temperature and rejects it to somewhere where there's high temperature. These are the infamous T versus S and P versus H graphs. Again, the 4 main subsystems are here. 1 to 2 is the compressor, 2 to 3 is the condenser, 3 to 4 is the expansion valve, and then 4 back to 1 is the evaporator. This is the apparatus we used. It's right behind us, back there. The fluid we use is Freon 22, and you can see the 4 main subsystems again. Where each number is located, right before each subsystem, is where we took our pressure and temperature measurements. Okay, the objectives for this lab, basically we wanted to perform a thermodynamic analysis on an air conditioning unit to kind of understand how it works. Then we can observe how the different charge levels of the Freon will affect the performance, and then do analysis of the system to calculate the COP. Then from there, calculate a few things: the Freon absorbed by the evaporator, the heat rejected by the condenser, the power from the compressor, and then the mass flow rate of the Freon. This is the raw data that was collected. We were able to do 4 runs before the Freon was completely drained from the system. You can see each 4 locations. Each measurement was taken before the subsystem, starting right before the compressor. And for all 4 runs, you can see that the measurements don't vary that much. We also took intake and outlet velocity for initial and final, and also took the inlet and outlet wet and dry bulb temperature also for initial and final. From the temperature and pressure measurements, we were able to find the enthalpy and entropy for each location at each run. And then I came up with a T versus S graph. And you can see it's pretty similar to the ideal T versus S graph for an air conditioning unit, as well as the P versus H graph. Then from those enthalpy calculations, I was able to find the COP for each run. Basically, the COP is coefficient of performance. It's the ratio of the benefit to the heating or cooling to what is expended, so the working compressor. So I found it for each charge, and it only varied around a 1/10 of a percentage. Okay, so to get all the calculations I said in the objectives, we first needed to find the mass flow rate of the Freon. Now to do that, we had to take the mass flow rate of the air, and then to get the enthalpies of what comes out and what comes in. And then from here, we had to find this using the psychrometric charts in the thermo book. And then once the Freon mass flow rate was found, we were able to calculate everything else, as well as the tonnage from the evaporator. So these are the results from that. You can see I did it for initial and final, and it didn't vary that much. I got a total tonnage for the initial at 0.86 and for final 0.81. And I researched that for a residential house or whatnot. Tonnage for an evaporator is usually around 1 to 5, so it wasn't that off. Errors that we could have come across: obviously human error, incorrect calculations, not waiting until the temperature and pressure measurement reaches equilibrium, and then obviously any calculations in grounding. And then if there were incorrect velocity in and out from the apparatus that we used. Okay, any questions?
Can you go back to your COP versus charge, correct?
Yeah.
It's, are you saying it's low?
It's inverted from what you would kind of expect, because you would expect it to be suboptimal at like 14 and a half, and then overcompensate at like 16, and then like 15 and a half would be near your optimal value ranges, where you have right now Freon to get the best efficiency out of the system.
Right.
So, thoughts on that?
That could have been, you saying it should have been higher?
I'm saying that instead of it dipping like that, it should have gone to a peak instead of a minimum.
Oh, like at 15, it should have been the highest?
Yeah, it basically should be flipped almost, shape-wise, not necessarily value-wise.
This could have been, I don't know, maybe I did an error calculation when finding the entropy and entropy, but I mean, these were the values that the thermo charts gave me, so. But we also had, like I know in the manual it said that when the Freon is fully drained, it should be around 10 or 18 pounds, where it said 16 when we drained it. So I don't know if that has something to do with it. Yeah.